This is Programme 3 of VideoTel's series on practical marine electrical knowledge. The series is made up of 8 programmes. Programme 3 deals with the main power sources and their circuit breakers, including synchronising, load sharing, fault-finding techniques and remedies. Also, test procedures on a circuit breaker if it fails to close normally. There are many system variations around, so it's most important that you become familiar with the components of the electrical system and the layout of the main switchboard immediately you join a ship. Pay particular attention to the layout of the emergency switchboard and the automatic startup system of the emergency generator. This study will pay dividends during a blackout or when troubleshooting the cause of a major breakdown. Now we must emphasize electrical safety. The golden rule is, before any work is done on an electrical installation, first isolate the circuit by removing the supply fuses or locking the circuit breaker in the open position so that the circuit cannot be energized accidentally. Then post a warning sign to alert others that the circuit is being worked on. Then prove the circuit dead with a voltmeter or an approved line tester. A switchboard can never be considered dead unless all AC generators connected to it are stopped, locked off, and all other supplies are disconnected. These points can never be emphasized strongly enough. The electrical rescue procedure is described in Programme 1. A typical scheme of power generation on board ship will have 2 main AC generators, or alternators, and 1 emergency AC generator. But there are many different designs depending on the ship's operating role. The most typical scheme will provide 440-volt 3-phase alternating current at a frequency of 60 Hz. Some ships will have 380-volt 50 Hz systems. There are also high-voltage systems of 3.3 kilovolts and higher in existence, where size and power-to-weight ratio of the equipment is a crucial consideration. Some ships have shaft generators fitted for use when the main engine is running at full speed. The prime movers for the main AC generators may be either steam turbines, diesel engines or gas turbines, although one of the AC generators providing mains power must be driven by a diesel engine. The emergency AC generator is driven by its own diesel engine, which is set to start automatically if a failure of the main generated power is sensed, usually a loss of steam pressure, voltage or frequency. This drawing shows the circuit arrangement for a typical emergency AC generator starter panel. The supervision circuit senses the loss of the main electrical supply. The sensing relay initiates automatic run-up of the emergency diesel via the control circuit supplied from the emergency batteries. Alarms and indications for high temperature, low lube oil and loss of coolant are also powered from the emergency supply. A similar system is used for auto-starting the standby diesel alternator. The starting system must be tested regularly with the alternator and a load, such as a fire pump motor, connected to the emergency switchboard. The system shown here is a 110-volt system and has its own testing circuit incorporated. Engine starting may be by battery, air pressure, hydraulic, or inertia initiated. Check your own ship's diagrams for specific circuit details relating to your auto-start equipment. Now we'll show you the synchronizing of 2 AC generators. One of the most frequent operations required involves connecting an incoming AC generator or alternator to the bus bars, which are being supplied by another AC generator. This process begins with starting up the prime mover, in our case a diesel engine. The engine is run up to speed, then the exciter current is increased until the alternator's output voltage reaches that on the bus bars. Here it is 440 volts. Being an AC system, the voltage, the frequency and the phases of the incoming supply have to be identical with those on the bus bars before the incoming alternator circuit breaker can be closed. When the required voltage is reached, a synchroscope is switched in. A synchroscope and phase indicator lamps show the phase shift between the two supplies. The speed of the incoming alternator is further increased for the output to reach the required frequency. In our case, 60 cycles per second. Continue adjusting the governor of the prime mover until the frequencies are identical and the phase rotation is synchronized. Here, on the bottom half of the synchroscope, the pointer shows when to close the incoming alternator's circuit breaker. The phase rotations are synchronizing. Now the button can be pressed and the circuit breaker closed. The two alternators now provide power in phase with one another. Most synchroscopes use the 12 o'clock position of their circular display to show the point of synchronization. The synchronizing equipment can now be switched out and the load shared between the two alternators. The governors of the two prime movers can be adjusted so that the two alternators will take about equal share of the total load, as shown on the kilowatt meters. Synchronizing is carried out on each occasion when a ship enters or leaves port or operates in confined waters, or when power needs arise which may overload a single AC generator. The total load will vary as the power demand of the ship alters, but the two AC generators are set to share it equally. We continue with automatic voltage regulators, AVRs, followed by testing a reverse power relay. The output voltage of the AC generator will be controlled by automatic voltage regulators in accordance with the changing power demands. AVRs are electronic devices which adjust the exciter current of the AC generators to maintain supply voltage at 440 volts as the various loads are added to or reduced. Voltage fluctuation without apparent reason is one of the symptoms of an AVR becoming faulty. If the voltage settles down on switching to manual voltage regulation, the automatic voltage regulator should be investigated and possibly replaced by a spare one. An alternator is protected by a number of devices, such as overcurrent, short circuit and under-voltage trips in the circuit breaker. Additional protection is provided by the reverse power relays and preferential trip relays. Their function is to monitor the power supply between an alternator and the bus bars. If the power flow is reversed from the bus bars into the alternator, the reverse power relay disconnects the alternator from the bus bars. The reverse power relay must be checked periodically by reducing the speed of the prime mover until the reverse power relay has operated. This point is preset at a few % of the full rated generator output. The settings are different for diesel or steam turbine prime movers. If, for any reason, the reverse power unit of an alternator malfunctions, the alternator must be under constant watch while running in parallel. The preferential trip relay will shed non-essential loads if the alternator is overloaded until normal load condition is reached. Other protective devices for the AC generator are housed in the circuit breaker. They are under-voltage and overcurrent relays and short-circuit trips. They disconnect the AC generator from the bus bars if either a severe and prolonged voltage drop occurs, or the AC generator is overloaded, or a severe short circuit occurs on the system. Now we shall see some typical tests. Most electrical superintendents and chief engineers like to leave the AC generators and their voltage regulators well alone in normal circumstances, but occasionally some tests and repairs have to be carried out. Insulation resistance and continuity tests of the alternator windings and feeder cables can be conducted from the incoming side of the generator breaker at the switchboard. Remember always to use a rubber mat for safety when working behind the switchboard. For the sake of measurement accuracy, the instrument fuses, the indicator fuses, and the control circuit fuses must be removed. Then the insulation resistance tester is checked. Two good earth points must be found. Then the phases can be checked to earth. If the insulation resistance values are checked, these can be recorded and the resistance trends monitored. Faults which relate to exciter failure can be tested either at the terminal box, or slip rings, or rotating diode ends. We show you here some typical procedures to follow if, for instance, the AC generator fails to generate the 440 volt AC output. A possible cause for this is the loss of residual magnetism in the rotor poles of the AC generator, or in the field poles of the exciter. 3 or 4 torch batteries in series will provide enough DC current with which to flash the AC generator at the appropriate point. This should re-establish residual magnetism. The manufacturer's drawings will show the correct polarity. If this procedure does not produce the required result, shut down the prime mover and lock off its controls. If the need arises for further tests, an important point must be kept in mind. An insulation tester must not be used on an electrical circuit which incorporates electronic components such as diodes. These must be shorted out before any insulation resistance readings are taken. Here, the field coils are tested to earth. Note the correct procedure being followed. First, the tester is checked, then 2 good earth points established, then the actual tests are made. Tests for possible faults in the exciter field coils are carried out at the terminal box. Here we see the coils being tested to earth. Again, the correct procedure is followed. First, the insulation resistance tester is checked, then 2 good earths found, then the test carried out. Testing for open circuit fault can be done with a multimeter. The procedure here is, first check that the circuit is dead using the multimeter set to read voltage. Then disconnect the feed wires from the coil ends, making a note of the color coding of the wires so that they can be reconnected correctly. Then set the meter to read resistance. The test can then be done, testing the meter first, then the terminals. The reading shows good continuity. A break in the continuity would have left the pointer at infinity. Now the contacts are remade and the terminal box closed. What if the excitation is working well, but the AC generator still fails to generate AC output? This fault, if it occurs, usually shows up when an AC generator is started up, ready for synchronizing with other units. If you have no meter indication of excitation, you will need to test the exciter, as shown just now. With some designs of static exciters, the check can be made at the automatic voltage regulator. After the circuit diagram has been studied. These exciters would not produce a DC output if there was no AC output. Here, the ammeter shows that the exciter current is high, very high. Yet there is no AC output. So, first switch to manual voltage regulation to see if a fault exists in the automatic voltage regulation. No, the excitation current is just as high and not easily regulated. Shut down the machine and consult the circuit diagram. The output of the exciter goes to the rotor coils through a diode rectifier system, and the coils are in parallel with a diode surge protection system, here made up of a capacitor and a resistor. Their function is to stop any voltage spikes damaging the diodes. In order to test for a possible short circuit fault, the high excitation current suggests this, the three circuits must be separated and tested independently. This means the alternator must be opened up to reveal the wiring involved. Here we've stripped out the alternator rotor for easy demonstration. But of course, there's no need for this when the job is carried out. In practice, first separate the wiring to disconnect the diodes, the capacitor, the resistor and the rotor coils. Here this has been done already. Now measure the diodes in both directions. All diodes must be checked, but we show only one here. Then check the capacitor, which in this case is built into the rotating disc. The pointer shows that the capacitor charges up from the internal batteries of the meter. This indicates that the capacitor is all right. The test is done in both directions across the capacitor. Now the resistor. And there is the fault. The meter shows a short on the resistor. On this machine, the resistor is built into the rotor shaft, so that there's no question of a simple and quick repair. Reconnect and run the system without the resistor, but have it replaced as soon as possible. We now move on to the AC generator's circuit breaker. We describe its function and show what to do if it fails to close normally. An AC generator circuit breaker is designed to connect the AC generator safely to the bus bars, as well as disconnect it automatically if serious malfunction occurs in the system. Here is a solenoid-operated air breaker with undervoltage relay and trip. A set of auxiliary contacts, the closing link mechanism, the closing coil solenoid, overcurrent relay, and a set of fixed and moving main contacts with their arc chutes. The main contacts are closed under spring pressure, which wipes the surface of the fixed contact points, ensuring good electrical contact. These contact points are plated and must not be greased or cleaned with abrasive material. Generator circuit breakers are set for correct function at the factory. By way of routine service, all moving parts should be lightly oiled. If, for any reason, a circuit breaker does not function normally, first try and close it manually in the test position when it's safe to do so. If it closes and holds in, this indicates a fault in the closing coil circuit. If it closes but fails to remain closed, the no-volt coil circuitry may have a loose connection or other fault present, perhaps in the DC transformer rectifier unit. Withdraw the circuit breaker into the full-out position and disconnect the control wiring and plugs. Test the appropriate circuits for faults. Always test that the circuit is dead before testing for continuity. The manufacturer's diagrams must be consulted for checking the circuitry. There is a set of spring-loaded plugs at the rear of this circuit breaker. Check that they are free-moving and connect properly. Test the no-volt trip and the closing mechanical linkage by holding the no-volt armature down, closing the breaker manually and letting the trip go. If the breaker fails to close, the most likely causes are a loose connection, a sticking trip button, or the overcurrent or reverse power trip contacts not resetting properly. Alternatively, an open circuit fault has occurred in the closing coil circuitry or due to malfunction of the power supply to the closing coil. Well, this concludes the subject of Programme 3. We've discussed a typical mains generating system and the automatic startup feature of an emergency generator. We've shown how to synchronize two AC generators and how to trace and test for a fault in the excitation circuit. We then showed how to reinstate residual magnetism and how to trace a fault in the AC generator rotor. Finally, we talked about an AC generator circuit breaker and dealt with fault tracing on a circuit breaker if it fails to close normally. We recommend that you watch this program again and that you consult the book Practical Marine Electrical Knowledge, which accompanies this series and will allow you to study certain aspects in greater detail. Finally, here's a list of contents for all the programs in the series.